Okay, good morning, everybody. Okay, so what we are going to cover today is we're going to go over three forms of advanced hashing. The first one we're going to go over is what's known as a quadratic hash, and it gives us a more distributed way of being able to put elements into keys than just a conventional double hash. The second one we're going to go over is one called Robin Hood hashing, where the idea is that instead of going and looking for the next location of an element we're going to hash, we'll hash that element to the first location and take the element that was previously there and hash that to the second location. And with the goal being that the elements that we have most recently hashed are also going to be the elements that are most likely to be able to be found without a collision. The third one we're going to do is we are going to do a cuckoo hash combines all of these elements into one big hash with the goal of being able to allocate a certain amount of memory and be able to take up a lot of the slots before we have to rehash. So up to this point, what we have learned about in collision resolution is that there are two main ways of doing this. We could do separate chaining, which is we would put elements into a linked list or a dynamic array in each bucket with the objective of being able to just say, well, if you find this particular collision, then you can search through the array. It was supposed to reduce some complexity. And then we found this idea of open addressing, where we allocate an amount of memory and we would go to a specific bucket and we would use our hashing function to be able to get to a specific location. And so in class, we learned about linear probing, and then you did a creativity challenge where you took that concept and you moved it to a double hash where you implemented your knowledge of inheritance and function. So the next thing I'd like to show you is this idea called quadratic probing, where what we're going to do is we're going to continue to iterate. But what we're going to do is we're going to take the result of the previous hash if we have a collision, and then we're going to add a quadratic result here. And so what's going to happen is C1 and C2 here are constant values, and I squared are going to be the value of the iteration. So we start out with the iteration at 0, and that just gives the hash function. Then we have our result of that hash function, and we add that with Ci times I plus C2 times I squared. And we want to pick numbers that, and these are common choices, and the reason why is because if we have 1/2, there we go, 1/2, and we're adding 1/2 squared, if we're doing plus 1/2, let's say we're doing iteration 1 here. So it's 1/2 times 1 plus 1/2 times 1 squared. So that comes out to be 1. If we have to go to the second iteration, this becomes 1/2 times 2 plus 1/2 of 2 squared, which is going to give us 1 plus 2, because it's going to be 1/2 times 2 is 1. 1/2 times 4 is 2, and that's going to give us 3. And if we do this with the third one, we're going to do 3 squared. This is going to be 1.5, and it's going to be 9 divided by 2, which is going to be 4.5, and that's going to come out to 6. So in every single iteration, the way that those variables are chosen ensures that we will get a whole number at the end when we calculate it out. So therefore, we are able to obtain a deterministic relationship with the element in the hash. And so this is better at even double hashing and avoiding clustering, but it can miss empty buckets. And so linear probing is the opposite. It doesn't miss empty buckets, but it is susceptible to clustering. So here I have the equation that I would have in code. my offset. So we're iterating through. We have the iteration is going to start at 1 after the initial hash. Current position is equal to current position plus the offset, which I've calculated here, mod the array size, which is this last part here. We make sure that we still get it into the size of the bucket. And then we increase the iterator. And then if that is not empty, or it's not a location defined, then we just move on to the next iteration. Does that make sense to everybody? So I'm going to go through 2 examples of quadratic programming and quadratic probing. And I'm going to also ask you all what you think would happen in certain situations. So we have an initial hash table with 7 buckets, and the function is just value mod 7. It says draw the final table using open addressing with quadratic probing for 76, 40, 48, and 5, where C1 is equal to 1/2 and C2 is equal to 1/2. So the first thing we're going to do is we just say, well, 76 mod 7, that's the first iteration, and that's going to give us 6. So that's free, so we just put it in there. So we do 40 mod 6 is going to be 5, and that's going to put us in there as well. And then we're going to have 48 mod 7. So what's going to happen is 48 mod 7 is going to be 6, and it's not free. So we're going to go to our next iteration. This is where we start accounting for the quadratic hash. So then we take the value 6 here, and we say 6 plus 1/2 of 1 plus 1/2 of 1 squared. So that's 0.5 plus 0.5. And so that's going to give us 6.0.5 plus 0.5. It's going to give us 7. 7 mod 7 will be 0. And so that's going to be free. All right, so now we get 5 mod 7, and again, we are full. So what do we think is going to happen here? What's going to be the next step? And let me press escape so that way those of you in the chat can participate as well. What's going to be the first number that we're going to calculate here now that we know that 5 mod 7 is not, it gives us 5, is not an open space in the quadratic hash? Anybody want to give it a try? Yes, sir. Very good. Exactly right. Mm-hmm. Very good. Very good. So this is going to be 6 plus 1. That's going to give us 7 here. Plus 1/2 of 4, which is 2. This is going to give us 9. So 9 mod 7 is going to be 2. So it's going to be there. Absolutely right. 100% correct answer. So for those of you who are in the chat, I couldn't quite hear the response in class. Here's what was said. Initially, because we're going to take that initial value, we're going to say 5. The first iteration is 1, so it's going to be 1/2 times 1 plus 1/2 times 1 squared, mod 7, which is 6, and that's not full. So we take 6, and then we do 1/2 times the second iteration plus 1/2 times second squared, and that's going to give us 9. 9 mod 7 is 2, and that available bucket is free. Okay, so that 100% correct answer. Good job. So 55, we're going to go through the same thing. We go here. It's not in 0, but then we get to the second iteration, just like before. That goes to 3, and it's free. So now we have put in all the elements into the bucket. All right, so now I would like the class to direct me and tell me what we think the answer is going to be for this problem. So this is the same thing. We have a quadratic hash with 7 buckets, and the function is the value mod 7. We want to draw the final table using open addressing with quadratic hash for 22, 17, 15, and 8, with C1 is equal to 1/2 and C2 equal to 1/2. All right, so who wants to take the very first stab at it? What's the very first thing we're going to do? Yes. Mm-hmm. Okay, so then we do that, and then, so we get 22 on the output, and then what's going to happen? Very good. So we're going to mod by 7, so 22 mod 7 is going to be 1. Very good. So now we're going to do 17. So what's the step here? Okay, so we have, let me bring things up let me bring up the chat as well. So 22 mod 7 is 1, so Fang Kong and Brandon. 17 is going to go to 3, because we're going to do, so Fang Kong is absolutely right, because 17 mod 3 is 17 mod 7 is 3. So Fang Kong and Brandon are both absolutely right. So now we're going to do 15. So what's 15 here? Yes. Yep. So that's the first step here. So very good. And so in the chat, Brandon and Brandon and Kiani are both incorrect. So we'll keep working together. So keep going. I'm sorry. I apologize for interrupting. Mm-hmm. Very good. Absolutely right. So we see then in the chat that Tiani's come up with the exact same answer. So that is exactly right. So we have 1 plus 1/2 times 1. So that's the first iteration, plus 1/2 times 1 squared, which we mod 7, and that gives us 2. All right, so now let's do 8. So very good. That's exactly right. Let's do 8. What should we do with 8? Yes. Mm-hmm. Very good. So it's going to be the same example. So we're going to have 1 plus 1/2, and I think that's what Tiani and Fang Kong are saying here. So that's what's going on here. 1/2 times 1 plus 1/2 times 1 squared. So that's going to give us 1 plus 1 is 2, and it's not there. And so Fang Kong is giving us the full description of what's going to go on. So I'm going to describe what he's described. His answer here is 8 mod 7 is 1, 1 is full, goes to 3. So 1/2 is going to be 0.5 here, and 0.5, so that's going to go to 2. And so 2 is full. And so now what's going to happen here is now we go to the second iteration. 2 plus 1/2 of 2 is 1, plus 1/2 of 4 is 3. So we get 2 plus 1 is 3, plus 3 is 6. 6 mod 7 is going to be 6, and so that's why 8 is going to go into the bucket of 6. Okay, does everybody understand that? Yes, question. Yeah, these are always going to be the same. So it's going to be, you'll be given C1 and C2, right? So that's where the half is going to be. And then if, as was described a little here earlier, what's actually happening is it's going to be 8 plus 1/2 times 0 plus 1/2 times 0 squared mod 7. If that was our initial iteration, that's what's actually going on underneath the hood. And so that becomes 8 mod 7, and that's 1. And so what happens next is we go, well, that's not full. So now we increment iter, and now this becomes 1. And so that's where, but the difference is instead of using 8, we are updating with the solution from the previous iteration. So that becomes 1. Is it? I see. That's where I saw the light bulb go off. Okay. Any other questions? Yes. It's a little, I don't want to go too much into answering specific questions. So for those of you in the chat, the question is, why are we updating this? There's a lot of mathematics behind it. The objective is to ensure a better distribution. So by going to that specific one and moving off of it, it reduces the probability that we would end up going to that same key. And there's a lot of math behind it. This semester, I cannot assume completion of discrete math, so forgive me. I'd be happy to discuss in a lot more detail in office hours. Hey, are there any other questions? Okay, so here are the benefits and drawbacks, and this might actually help describe a little more. More distributed keys than linear probe and double hash. And so what I was referring to is that we can actually fill up 67% of the bucket of the hash instead of 50% before we're going to have too many excessive collisions. And so that's our goal here for trying to do it this specific way. However, it can take a little more time to calculate. So for those of you taking logic design and computer architecture, you're basically just performing several additions in order to get a multiplication, right? So using the quadratic and using multiplications there can actually degrade performance of that. And we've seen a couple examples of this in lecture. In particular, we learned all the way back in the beginning of the semester that the power method in C++ that calculates the power, it's actually recursive. And so sometimes when you're using recursion, it can incur penalties in terms of amount of memory used on the instruction stack. Okay, so does anybody have any more questions about quadratic probing before I go into Robin Hood hashing? Okay, so Robin Hood hashing is kind of like double hashing, except we're still gonna have two hash functions, but instead of putting in the first element and saying, well, it's not there, we gotta find where that first element is next, what we're gonna do is we're gonna take that element that was previous there, we're going to rob from the rich and give to the poor. And then what we're gonna do is we're gonna move along and we're gonna put this in the next location. So the whole idea is that we are going to displace the previous value and we hash the old value with the second equation. So the benefits are, if we're trying to take advantage of this temporal and spatial locality, we kind of briefly touched on it when we were talking about splay trees. But one of the things is if we hash something, we are going to tend to try to hash it again soon or something that's close to it. So what we're doing with Robin Hood hashing is that when elements are moved and replaced with a more recent one, the elements that have been more recently hashed are less likely to have to go to a second iteration. They're going to be there when we want to look it up the first time. Does that make sense? So that's one potential benefit of Robin Hood hashing. And therefore, that makes it cache friendly and memory efficient. All right, so let's go through a couple examples of that. So I'm going to move the chat over here and move Epic Pen over here. And so what I would like to do is I want to move through and I want to do two hash functions, show the insertion for the following elements, 21, 7, 18, 44, and 93 for a Robin Hood hash. So what do you think is the first thing we're going to do here? So we have 21, what are we initially going to do? Yes. Very good, 21 mod 7, so 21 mod 7 is 0, so Fang Kong is also correct. So we see that, why did I do 21 mod 11? Okay, I apologize for this. Well, I guess I just put in 11, now we're doing 21 mod 11. So 21 is going to go to 10. And so what's going to happen next is that 7 mod 11 is going to go to 7, like so. So here, just to make it less confusing, I'll put 11 there. And now what's going to happen is we're going to do 18. 18 mod 11 is also going to give us 7. So now what we're going to do is we are going to replace 7 with 18. And now 7 has been moved out. Did everybody see that? So now what we're going to do is we are now going to go to the second function. So 7 mod 7 here gives us 0. A better function, and again, I apologize, but a better function would be 11 mod 11. But in this case, it's probably going to stay 7 mod 7 there. So for 44, 11 mod 11, you know what? I'm just going to copy and paste this, and we're going to work through it together on a whiteboard as though we were doing this on an exam together. Okay, so let me go down here. And I'm going to make this K mod 11, and we're going to make this 11 mod 11. And so what we're going to do is we'll say 21 mod 11 is going to give us 10. So we would have 0, 1, 2, 3, 4, 5, 6, 7, 8. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So 21 mod 11 is going to give us 10. Then we're going to do 7 mod 11, which is going to give us 7. Then we're going to get 18. So 18 mod 11 will be 7. So what we would do here is we're going to take 7 out. 7 will be our next value, and then we put 18 here. Then we're going to get 7 mod 11, right? And that's going to give us 7. And so now we have a problem here. And so then we would end up rehashing. I apologize for this. Let me make this 8 just to be clear. All right, so 21 mod 8 would give us 8. 18 would be 7. 44 mod 11 is going to be 0. 93 mod 11 is going to be 5. Yeah, it's going to be 5, so it'll be 93. So let's add a few more and see what's going to happen here. So to modify our problem even further, I will say, all right, let's do 25. So now 25, what's going to happen is 25 mod 7 is going to be 4. And if we added 15, let's do 15. Okay, so 15, I'm having a rough morning, I apologize. 25 mod 11 is going to be 4. 25 mod 11, I'm struggling. 20, 11, 22, yeah, very good. And now let's do 16. We're gonna do 16 here. All right, I apologize for that. So 16 mod 11 is gonna give us 5. Everybody see that? So here's what the Robin Hood hash will do. The Robin Hood hash will go here and say, well, 93, it needs to be taken out. And then we're gonna put 16 in there. Right? And so 93 is going to be our next thing. So 93 mod 11 on low, that will be 8. And then we would look here, and then 8 would be there, right? And eventually, we would get into this position. Did everybody see that? Which actually leads me right into one of the issues with Robin Hood hash, is that with a Robin Hood hash, you can get into cycles pretty easily and potentially require a lot of rehashing. So what's going to happen is we can reduce the amount of memory and do it efficiently and try to reduce the need for probing. And that is what's going to come into what's going to motivate the remainder of our lecture today. And that's going to be what's called a cuckoo hash. So cuckoo hash builds off this idea of Robin Hood hashing, but it's also going to have 3 dynamic arrays. We can have at least 2, but you can get up to 91% of the hash being full without having to worry too much about actually rehashing and having to rehash the entire table until you get to approximately 91% of the hash. Before, we had to do 50% before we started having real issues. So where the motivation for cuckoo hash is, this is the cuckoo bird. And the cuckoo birds can be vicious. What they'll do is they'll go into, they'll find a nest of another cuckoo bird, throw all the eggs out, and then put its eggs in it. So they're pretty vicious, and that's where the idea came from when Paul and Rodler named it. And their goal is there's no need to allocate new tables for the rehashing. We simply run through the tables to delete and perform the usual insertion procedure on all the keys that are not at their intended location. And so let me show you what I mean by this. So we use at least 2 hash functions. And if the first one is empty, put the element there. If the second one is full, what we need to do is we take the previous one, we have a second hash function and a second array. And in the example I'm going to show you, we're going to use 3. And so what ends up happening is we could potentially encounter a cycle with 2. So the best way to do this is we're going to add in a third dynamic array. So what I'm saying here in the slide is that both locations are full, and we would bump the key value pair. But if we keep going back and forth, and we encounter the same location twice, that's when we would need to resize and rehash the table. So if we get to a situation where we can't go through and we just gets locked, then we would rehash. And so the way that this was avoided, and I have this paper here, and this is kind of what I was referring to a little earlier. I want to include this link to those of you who want to read into the mathematical derivations as to why this thing works. It's a little outside the scope of the course, but you can go from having cycles cause you problems with 52% in a normal hash table, which is why we have to redouble once we reach half of the size of the hash. In a cuckoo hash, when you have 3 hashes, we can fill it up to 91% before we start running into serious problems. So what I would like to do is we have 3 hashes, and how I'm going to conclude lecture is we're going to go through 2 different problems, the type of problem that you might encounter on an exam. And the whole idea is we have 3 hash functions. Here it's just k mod 7, here it's k divided by 7 mod 7, and here it's k plus k divided by 7 mod 7. So we're just going to use the value instead of doing what quadratic probing does, which is to use the updated locations. So when we do 42, 7 mod 42 is 0. And then we're going to do 93, so 93 mod 7 is 2. And then we're going to do 79 mod 7, which is 2. So now we're going to have our first thing. So it's going to do what we would do in the Robin Hood hash, which is we would take out 93 and put 72 in that position. Does that make sense? So now what we're going to do is we're going to say, well, 793 divided by 7, and that value will be modded by 7 and will be placed into the second bucket. So what will happen is 93 mod 7, that will give us 13. 13 mod 7 is 6. Then we'll put in 11. 11 mod 7 is 4, so that ends up in the first hash. Then we're going to do 22. 22 mod 7 is 1, so that's going to be 1 in our first hash. And then we're going to get 34. That will be 6. And then we're going to get 9. 9 mod 2 is going to be 2. So what do you think is going to happen here? Any ideas? We have a comment in the chat. Replace 72, very good. So we're going to replace 72 and move it up. So now 9 is at that location in the hash. So now what do you think is going to happen? What do we need to do in order to hash this value? What do you think? So we have 72. What should we do with this cuckoo hash? Yes. So 72 is going to be divided by 7, and that's going to be 10, right? Mod 7, which is going to give us 3. So that notation there, k divided by 7 with the low brackets, means divide it and then give me the lower value, meaning that it's not going to be up. If it was above, it would be 11, but below it's going to be 10 because we have 10 with a remainder. So now we have 44. 44 mod 7 is going to be 2. So now we're going to push 9. And now 9 is going to be 9 divided by 7, which will be 1, mod 7, which will be 1 in the second hash. So now we have 44, I'm sorry, not 44, 15. 15 mod 7 is 1, so we're going to push 22 out of its bucket. And then 22 divided by 7 is going to be 3. So 3, we're going to put 22 in bucket 3, and we're going to bump out 72. Does everybody see that? So now what we're going to do is we're going to say k plus k divided by 7 mod 7. So what this gives us is an offset in order to mod. So 72 divided by 7 is going to be 10. And that's going to be 72 plus 10, which will give us 92. And then we'll do 92 mod 7, which will then be put into the third array. See that? So we have 72, we got 10 from here, then 72 is k, mod 7, and that gives us 1. Does anybody have any questions about that? So now what I want to, let me bring up the chat here. So we're going to work through the same thing here. Move 3 into the second bucket. So now we have another problem, and this one's a little longer, and the objective is to see what will happen when we have to go past the third bucket. Okay. Does everybody see? So what we're trying to do is how does cuckoo hashing avoid cycles? So first we're going to have 15. So what do we think is going to happen? So someone quickly tell me what's going to happen with 15. Going to go into 1. Very good. So it'll be 15 mod 7 will be 1. What about 19? Very good, it's gonna go into 5. Now we're gonna have 34. So what's 34 gonna be? 6, very good. Now we have 7. So 7 mod 7 is gonna be 0. So we're kind of quickly filling up this first hash. So 16 is going to be 2. 17 will be 3. So now we nearly have the entire first array full. So now we're going to go to 21. So what do we think is going to happen here with 21? So very good. So 21 will move into 0. And so what do we have to do here? So that will move 0 up there. So now what are we going to do with 0? Very good. So that'd be 0 divided by 7 gives us 0. Mod 7 will now be 0. So now we're going to do, so we just put in 21. Now we're going to do 26. Sorry. So what do we think is going to happen with 26? (26) replaces 19. Very good. So they're absolutely right. So Fan Kong is right. 26 replaces 19. So now what are we going to do here? So we have to do something with 19, right? Yep, same hash function. So wait, 19 goes into 2. 19 divided by 7 is going to be 2 mod 7, which will be 2. Very good. All right, so now we have 9. So 9 mod 2, we're going to push 16. And so now what are we going to do with 16 here? Hey. 16 replaces 19, very good. So 16 divided by 7 is going to be 2. 2 mod 7 is 2, and then we're going to replace 19. So that's absolutely right. So now that we have 19, we are going to do 19 divided by 7, which is going to be 2. That's going to be 19 plus 2 inside, and then that's going to be 21 mod 7. So that means 19 is going to go there into 0. Does everybody see how I derived that? All right, so if there's any questions, please feel free to ask. So now we're going to do, see, we put in 9, we got to put in 31 now. So 31 mod 7 is going to be 3, so we're going to bump out 17. So now what do we do? Okay, so he's 17 divided by 7, that's 2, so we're going to replace 16, very good. So now this is where this idea of having k plus k divided by 2, so we're getting an offset from the initial number, and that'll help us resolve some collisions there. So 16 divided by 7 is going to give us 2, 16 plus 2 is going to give us 18, 18 mod 7 give us 4. Okay, so 4 is the one last empty bucket in the initial thing. So here I'm kind of setting up what we might have to do if we get another cycle. So let's walk through 23. What are we gonna put 23 first? Yep, be 2, so we're gonna bump out 9. And so now what do we do with 9? So Fan Kong is right, 6 replaces 9. So what are we gonna do with 9? Yep, very good. And so it's gonna be 9 divided by 7, which is 1 mod 7, which is gonna put it in there. And so now we have the last number. and this is going to be 11. So 11 mod 7 is going to be 4, so we're going to bump 4 out. 4 divided by 7 is going to be 0. So we're going to bump 0 out. And then we're going to say, well, 0 plus 0 divided by 7 is 0. 0 mod 7 is going to be 0. So now we're going to bump out 19. Everybody see that? So what do you think we're going to do now? What do you think we should do? Any guesses? Okay, we could add another bucket, but the thing is we want to be able to keep going until we fill up 81% of the hash. So while that's a good guess, you kind of have the right idea, but we're not going to add any size. What do you think we should do here with 19? Yes. Absolutely right. So we're going to go through the process again. So we're going to do 19 mod 7, which is going to give us 5. Now the crucial thing is it's going to bump out a different bucket than we did before. So we're going to bump out 26. So we start again with 19. So now we bump out 26. And so 26 divided by 7 is 3. And 3 mod 7 is 3. So now we find another spot for it. Yes. Yeah, these are pretty standard. They give pretty good distributions. That's why they're generally chosen this way. And the crucial thing, so here's a good way to think of it. Again, I want to avoid some of the mathematical. Here it's initially, all right, we have 7 buckets, we do mod 7. We can just put them in there and we choose a prime number because we can't assume that what the user is going to put in is going to be distributed. So prime improves the distribution. So here would be like, okay, well, it wasn't in there. Now we're going to choose a second one. Now let's divide it by 7, and that is going to give us, instead of just relying on the remainder, we can also have the result and then use that as the remainder. So that would, for example, 21, I'll say 24 divided by 7 is going to be 3 with a remainder of 3. So the first time we chose this one, the second time we're choosing this one. So then it's like, okay, well, that one didn't work. Well, now I have 24. Let's use that calculation we did as kind of an offset. So 24 divided by 7 would give us 3. So let's say 24 plus 3 mod 7. And so that becomes 27 mod 7. So now we're coming up with a different number. Okay, so that would put it into 6. Did that address your question? Okay. All right, so a question is 91% distribution resulted by this a specific set of hash functions? Yes, I used the functions that they used in the chat and in the paper. It depends on the function. So there's a lot of research going into the right type of functions that you might want to use to do improve hash functions for specific tasks that you might want to do. And that's more of a, there's actually courses in grad school that you could actually pursue that really go into the mathematics side of it. But these ones will provide the 91% distribution. Cool deal. And here's the interesting thing with 19, because we went through a whole cycle, all of these elements are now, would be found first, second, and third. So one of the benefits of the cuckoo hash here, move this, is that we see that our likelihood of finding something in our first time through is significantly higher. So not only can we reduce the amount of memory in order to be able to keep with this big O of 1, but when we do searching, we would find that majority of the elements are closer, so we've improved our search time as well. Does everybody see that? So just to conclude, the benefits of cuckoo hashing is because there's more location and better distribution, requires fewer rehashes. It's much faster for probing small cache resident hash tables on modern processors. And because the elements can take up about 90% of the buckets without a rehash, the memory is going to be reduced. So it offsets some of this burden that we've been incurring. And last thing I want to discuss, some of the drawbacks. So because of the cycles, some insertions may take more time than a normal linear probing algorithm. Double hashing reduces collisions by using 2 equations, and quadratic probing reduces collisions by randomizing the bucket through quadratic growth. And to hit here, and this gets back to the question, the whole goal is to try to randomize where we're going to end up. So before, if we were dependent upon the initial value and we were trying to do quadratic, that wouldn't be as randomized as if I took the result and put it in. So it's no longer dependent upon the previous value. So it gives us a more, the goal is to give us a more distributed set of keys to reduce the hashes. Okay, does anybody have any questions? All right, on that note, I'll give you all a treat and dismiss 4 minutes early today.